Hello everyone, my name is Kathan and today we'll be discussing the problem apple division from the introductory problems of the CSES problem set. Let's begin. Let me read out the question for you. So there are n apples with known weights. So there will be some weights associated with apples. Our task is to divide the apples into two groups so that the difference between weights of groups is minimal. So we have a set of n apples and each one of them weights, and we have to divide this weight array into two subsets, two sets, such that the difference between weights of the groups is minimal. That is, sum of weights in group 1 minus sum of weights in group 2. The absolute value of it is minimal. The input is first n, of course, and the next line has n integers. So this p1, p2, pn are the weights of each apple, and output is the minimum difference between weight of the groups, right? The optimal difference. That is, we have n apples, each one of them are weights. Now divide this weight array into two parts such that the sum of weights in group 1 minus sum of weights in group 2 is as minimum as possible, and that's what you want to output, the minimum difference between weights of groups. Constraints are like n is pretty less, so apples don't go more than 20. So this is also one interesting aspect, right? Constraints are less, so pay your utmost attention here. And then weight values, of course, 1 to 199, so they both are in integer range. But I'll come to this constraint, n's constraint, in a bit. And for example, here they have an input here, so 5 apples, and these are the weights given. Output is 1. Why? Because you can create a group 1 which has weights 2, 3, 4, total weight is 9, right? And we can have a group 2 which has weight 1 and 7, total weight is 8. So you can say this is the optimal partition which gives the minimum possible difference between the sum of weights among the groups. So here total weight was 9, weight is 8, so 9 minus 8 is 1. Fine, so I mean that's about this question. Let's go to the iPad and try to understand a bit more on this. The first thing that you should notice here is n's value. N is not more than 20. It's a very less value, right? So even if we have a, let's say, exponential solution, let's say you have a solution of complexity 2 power n, then the time complexity will be just 2 power 20, which is what? What is 2 power 20? Can you convert it to 10 power? How do you do it? You just simply divide it by 10 and multiply it by 3. So this gives you 10 power 6. So this 10 power 6 is very well within the constraints, right? So even if you implement the order of 2 power n solution, it will work. Fine. So with that out of the way, let's see what the question is asking. The question is asking that we have n apples, and there will be some weights given here, right? So there is weights here, p1, p2, so on, and we want to divide it into two groups. Let's call this group as z1 and call this group as z2. So let's say this z1 has m elements, right? And this z2 will definitely have n minus m elements, and we want to divide this groups in a way that summation, the absolute value of summation of this g1, or let's just denote g1 and g2 as sum of the groups only. So g1 minus g2, the absolute value has to be as less as possible, right? So we want to divide the weights into two subsets, or you can say two sets, such that the difference between weights is as less as possible. Now how less can you go? Like the less would be the 0, right? So the best case you can achieve is, if you can achieve g1 minus g2 to be 0, then it will be great, right? So try to you can say, try to get the sum to be as close as possible of both the set, right? So maybe if the total sum is t here, total sum means summation of, let's just call this as weight array w. So if total weight is summation of w, maybe just try that two sets have weight t by 2, t by 2. But of course this won't be possible always, because the elements can be anything, right? The elements can be like this, p values can be as high as 1e9, 1 to 1e9. So but fine, if you want the difference between sum of weights to be as less as possible, you will have to make sure that these weights are as close as to t by 2. Fine. So that's out the question. The question is as simple as it can get. Now how do you approach this question then? The first, you can say, the dumbest way that will come to your mind is a greedy approach, right? A greedy approach is bound to come to your mind. And what is that greedy approach? Maybe we can just we have this weights array, right? So this weights array w, and we have the weights p1, p2, so on till pn. Maybe we can initialize two group sums g1 and g2 to be 0. We can just go through the array, right? Go through the array, and we can assign a given element to a group depending on which group value is less. For example, I can just go through the weights, go through, let's say, for w in w, if G1 is less than equals to G2, that is currently the current sum of weights in group 1 is less than the second group, you just add this current guy to this group, else you add it to the second group, right? So effectively what you're doing is every time whenever you encounter an element, you're assigning it to a group with a lesser sum. Because the strategy makes sense. Why? Because what you're effectively doing is you're trying to keep the sum of two sets, sum of two sets to be as same as possible, as close to each other as possible. But this strategy has a fundamental flaw and it doesn't work. Why it doesn't work? Because you cannot reconsider your choices. So I'll show you. Let's say I have an array like the apples with weights 2, 3, 4, 5. And the greedy strategy, what it will do is it will try and put a apple to a group which has less weight at the moment, right? So we just make the pass through the array. So initially 2, like both weights are same, so you can just assign it to the first group. Then I'll go to this 3. I'll say which group has less weight, I'm gonna put it there. The idea is why are you thinking in this direction is, if I just put a current guy to the group which currently has less weight, maybe I can make sure that weight of both the groups will be as close as possible at the end, and I'll get the minimum possible difference, right? So you assign this 3 in thinking that if I put this 3 to the group which has less weight right now, I'm trying to make both the groups to be as same as possible, both the group sums to be as same as possible. So you'll thinking that you'll assign 3 here. Fine. Then you will come to this 4. Which one of them is less weight? G1, right? So you're going to assign 4 here. So 2 plus 4, 6. And then you will come here. 5, of course, you will have to assign it here because this group has less weight. So your thinking was, if I keep on assigning weights to the groups which has less weight as of now, eventually I might have two groups which have sums closer to each other. So what do we have here? So total sum here is 6 and total sum here you have 8. So the group difference is 2, right? So, but is this the optimal answer? Like, is the minimum possible difference 2? Actually not. This is not an optimal answer. Why? Because if you have the groups like this, let's say 2, 5, 2, 5 and 3, 4, this group sum is 7, this group sum is 7, so the optimal answer is actually 0. Right? So this was not an optimal approach. So the greedy strategy of assigning weights to the current group which is less weight does not work. Now you might argue, what if I sort this array and all, but like they have two fundamental flaws, like even if you sort the array or not. So this, if you sort the array in descending order, it might start to work in some cases, but they all have a fundamental flaw. So I'll write down the fundamental flaws that this greedy strategy has. The first flaw that we have is you are just assuming that if I make a local optimal choice, it will eventually lead to a globally optimal solution. But it is not happening here. And why it is not happening here is you don't have a ability to backtrack. Now what do you mean by backtrack? So this is a term you will hear a lot in, you can say, competitive programming or recursive based solution. Backtrack means you cannot reconsider your choice. Right? You cannot reconsider your choice. For example, once you have chosen 4 here, you don't have a way that, okay, I'll not choose 4, I'll instead choose 5. Right? The strategy is like, it's very rigid in the sense, if I am at a current guy, I will have to decide right now itself whether it will go to group 1 or group 2. Right? So this strategy, what we have here is, it's a very rigid one. Right? A very rigid strategy. So we don't have an ability to backtrack, or you can say reconsider our choices. So these are the two fundamental flaws. Local optimal choices are not leading to global optimal solution, right? The final optimal solution. Because what is a local optimal choice here? Assign a current guy to the group which has less sum as of now. So that was a local optimal choice, but it is not leading to a global optimal choice. We just saw. And we cannot backtrack. We cannot reconsider our choices. So these are two fundamental flaws. So if you cannot do these two, then what next? Now, okay, fine, greedy doesn't work, then what next? Greedy fails. If greedy fails, maybe just try brute force. Now what is brute force? The brute force is try every possible partition, of our weights array, right? So what do you mean by every possible partition? Let's say I have elements like this. Maybe just take the example of the CSES site as well, 32741. Let's say this is my weights array. So what is every possible partition? See, for this first guy, I have two options. Either it can be part of group 1 or part of group 2. For this second guy, I have two options. Either it can be part of group 1 or group 2. For this guy, I also have two options. Either it can be part of group 1 or group 2, and so on and so forth, right? So for every element, I have two options. For every element, I have two options. So 2 into 2 into 2 into so on, n times. So we have 2n possible partitions, right? 2n possible partitions. And this, if you see, you can say the number of subsets, right? This 2 power n, it resembles the number of subsets of this set, right? So what we have is there are a number of ways to divide a set into, divide this array into two partitions, turns out to 2 power n. And how? Because for every guy we have two options. So all in all, by the fundamental rule of counting, total number of partitions we have is 2 power n. Fine. So how do we implement this then? Now the implementation can be approached using recursion, and that's what I'm gonna show you here. But what we'll do is we'll build the, you can say, the recursive solution. Like how would you yourself come up to this approach? Then we can maybe focus on pseudocode and followed by the actual implementation code. So let me take an example here, and we'll see the recursion tree to get an idea of how the recursion can be implemented, right? So let's take 3 elements here, 3 apples. So 2, 1, 3. So I take, I'm taking a smaller number here because, like, see, you will have to consider 2 power n possibilities. So if I take a bigger example, then I will be left out of space. So we have 3 elements here. Fine. Let me index them as well. 0, 1, 2. We have 3 apples. What do we need actually? So for every guy, we have 2 options. Either it can be part of group 1 or group 2. So let's also keep track of what is the current group sum of 1 and 2. So maybe this is the group sum of like these are the variables are keeping track of what is the sum of group 1 and group 2 respectively, sum of elements in group 1 and group 2 respectively. Fine. So effectively what we can do is, if we have formed the partitions, we can just subtract that sum and maybe update the answer and so on. But let's not go too ahead of ourselves and focus on the basics. So our approach would be, for the first guy we have 2 options, for the second guy we have 2 options, the third guy we have 2 options, right? So let's make the choice of the first guy. So for the first guy, there's a guy at the 0th index. We can either include it in group 1 or we can either include it in group 2, right? We have 2 options here. So if we include it in group 1, what are you going to do is, you're going to add this 2 to G1, right? So G1 will become 2 and G2 will stay 0. Fine. Similarly, if you decide to add the 0th guy, the 0 index guy, to group 2, G1 is still going to be 0, but G2 is going to become 2. Fine. Simple. Now, now that you have chosen the first guy, so here you have made 2 choices. The second guy also you have 2 choices, right? The guy at the first index. So here I am making choices for the guy at the first index. You have 2 options, either including group 1 or group 2. If you added this first guy in G1, for the second guy you had options, 2 options here. If you had added to G2, again you will have 2 options here. So this will also span 2 ways. So here we can do it G1, G2 like this. So let's explore this. If you've added 0th guy to G1 and first guy to again G1, this is gonna be what? 3, 0, right? If you decided to add 1 again to G2, G1 will stay 2, but G2 will become 1. Now here, if you first added you can say the 2 to G2, and now you're adding 1 to G1, it is gonna become 1, 2. And if you decide to add again G2, then it's gonna be 0, 3. Fine. So if you observe this, like if you want to see how does the node values appearing, first you added 0th guy to G1, so that become 2. Then you added the first guy to G1 again, so that's why it is 3, and G2 is still 0. So if you want to see this 1, 2 value, you added the 0th guy to G2, right? Then you added the first guy to G1. That's why it's 1, 2. Simple, right? So let's move ahead. So now we have made choices for these two choices followed by these two choices, right? So that's why you can say 2 into 2, 4 nodes. These 4 nodes represent that you have made 2 choices here followed by 2 choices here, right? So these are all the possible ways to basically add first 2 guys. Now all that remains is to make choice for the third guy or the second index guy. Second index guy also you have 2 options here. You have 2 options here. Now what are these 2 options? Either add this 3 to G1 or G2. So if you decide to add to G1, it will become 3 plus 3, which is 6. This will still be 0. Or here in this will become 3, 3. Here again you have 2 options. If you decide to add 3 here, it will become 5, 1. Or in this case, it will become 2, 4. In this case, similarly, if you add 3 in G1, it will become 4. This will become 4, 2. If we decide at G2, it will become 1, 5. Similarly, if we decide to add to G1, this will be, I guess, 3, 3. And in this case, what is this case? This case will be 0, 6. So, like, if you just see this branch, it is like you are always adding to group 1. That's why it is becoming 6. And if you see this branch, you are always adding to G2. That's why it is 0, 6. So, this tree is sort of symmetric. And you can also observe a lot of repetitive problems. Bit hint into future videos of this playlist maybe. If problems are repeating somewhere here, you can use something called as a dynamic programming to save the calls and all. But yeah, forget what I said if you don't know. But yeah, just a quick heads up for dynamic programming here. But anyway, what you have effectively at the last level is you have all the possible partitions, right? So you have all the possible group sums for the partitions, right? For example, so these are, you can say 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, because you know you had 8 possible partitions, and these are the group sums for all the possible partitions. Fine. So I mean, yeah, that's about the recursion tree. But how are you gonna implement this then? How are you gonna implement this? To implement this, let's try to see the pseudocode. So maybe we'll call the function at the top level at this. We will of course need to pass the array. We'll need these 2 guys, G1 and G2. We also need a way to know where we are currently, right? So if we are at the, what element we have to consider next? Do we have to first consider 0th guy? If you have to consider the first guy, if you have to consider here the second guy, right? So we need a way to keep track of what is the current index we have. So a function, a recursive function, or you can do the solve function. Let's just call it recursive function f. It takes our weights array, the array. Then it takes 2 integers G1 and G2, which keeps track of what is the current group sum right now. And we also need to keep track of what is the element that we will consider now, right? And what do we do then? We can either add an element to group 1 or group 2. We can either add an element to group 1 or group 2. So we can either add an element to group 1. So in that case, weight array will still stay same. If you decide to add to group 1, that G1 becomes weight of I, right? And G2 still stays same, and consider the next guy. Fine. But you can also decide to add it to second guy. So G1 still stays same. G1 will still stay same. Or you can add it to G2 W of I, right? And consider the next guy, right? See, you can either add it to G1 or G2, and then you increment the index, because next time you have to consider the first guy. You can either add to G1 and G2, and then you increment the first, because you have to next time consider the second guy. Fine. So this f can be further decomposed into 2 parts. Okay. But what is the base case? Now this will go on happening. But what is the base case? So the base case will be when we have considered all the possible elements. That is, if maybe let me write a different color. The base case will be if I is actually equal to you can say n, right? I is actually equal to n, or you can say length of weights. Then this is our base case. So in this case, G1 and G2 will hold the weights of the current partition, right? So when I has become equal to n, so if you try to call it here, then I will become n, right? So now G1 and G2 is actually holding the weight of current partition, right? So in this case, maybe you can just update the answer here. right? Maybe we have an answer variable, a global variable, or maybe pass it reference. We can just update our answer max of I guess min, right? So min, because we want the minimum possible difference, min of answer and absolute difference of g1 minus g2, right? And maybe we can initialize the answer to a very big value initially, right? Maybe let's say 118 because like we have 1e9, so at the worst case it can be a very, you can say 1e9 into 1e9, the sums can be very big. That's why 180, safe bet. Or you can make a long max as well. Fine. So I mean, yeah, that's about the pseudocode, right? To find the partition, what you do is you either decide to add the first group or you decide to add the second group, right? But effectively you will have no elements to consider. So when you have reached the base case, you just update your answer. Alright, so that's about the recursive pseudocode, and like this can be easily converted to C++ code as well, right? Now what about the time complexity and space complexity, because that is going to be interesting. Now to calculate the time and space complexity, you have actually two options. You can either look at this recurrence and try to derive a recurrence relation, or you can look at the recursion tree and see how many calls are being made. Now this is a binary tree, right? So first layer has 2 elements, then it has 4 elements, so on and so forth. So the binary tree expands in order of 2. So all in all, you can say there will be 2 power n leaves, and even if you sum everything above here, so it will be 1 plus 2, so 1 to 2 power n minus 1, it will be not more than 2n. So effectively you can say you will be making about asymptotically 2 power n calls, right? So we'll be making 2 power n calls. And how much work do you do in every call? You just either add it to g1 or g2, right? So you don't do more than constant amount of work. So the time complexity will be simply order of 2n. Or if you want to see it another way, see here the recurrence will look like this. The time to figure out answer for n elements is actually equal to 2 tn minus 1, right? The time to actually figure out answer for n elements, you will have to make 2 choices and solve the problem for n minus 1 elements, right? Because you will incrementing I plus 1, right? So here you can see we are reducing the, you can say your search space to n minus 1. So this recurrence, I guess, is familiar to you. This is nothing but 2 power n only. So like, of course, you have seen 1 plus 2 n minus 1. They both are but nearly same. So this is 2 power n if you solve this recurrence. And yeah, I mean, that's about the time complexity. But what about the space complexity? We are not using any extra array or anything like that. So there will not be any external space like that. But you are making a recursive call, right? So this function is called this calls this, so on and so forth, right? But of course, at any given level, only one of the function will be executing in the recursion stack, right? So in the worst case, this guy is going to call this guy is going to call this, so on. So for n, calls n minus 1, n minus 2, so on till 1. So the recursion stack will have at the most, you can say, order of n stack frames. So the space complexity will be order of n, which is, you can say, the recursion stack space. Time complexity is simply order of 2 power n, because you have 2 power n partitions to consider, and for each one of them you are just doing some constant amount of work. That's the time complexity. So I hope you have understood the recursion and the pseudocode till now. So I'll move the coding part now, which will be very easy. But if you understood till now, please comment understood in the comment section of the video right now, and I can move on to the code. Okay, so here's the code. First I'm taking the input here, so n is number of apples. Then the weights array. So weights array I am taking long here for simple reason, like I know it was 10.9, but I just wanted to keep everything simple, so I took long. So whenever I see a range being 1e9, I just try to take it as long only, because it's very close to the maximum value of integer, right? That's why. So that's why I'm taking weights as long. Then I'm initializing this answer. So I could have kept it as global variable because I have to update it, right, whenever a partition is made, but I'll instead pass it as a reference in my recursive function, right? So I'll pass the weights array, the answer guy, as a reference. So any update to answer in this function which is made will be reflected afterwards, and I can just print the optimal answer, right? And then the start is basically the current index that you want to consider, the current element that you have to consider. So initially you will have to start with 0th guy, right? So for the 0th guy, you have 2 options, and we'll increment this as and when we make choices. And 0, 0, this is a group 1 sum and group 2 sum. Fine, and we'll print the optimal answer later on. So let's just go through this divide apples function then. So it's a very simple function. What it takes weights, Answer? The answer is very importantly by reference, because we are going to update it here. Index, the current element for which you have to make choice, either including group 1 or group 2, G1 and G2. So we have two choices, right? So add current applet to the G1. So in that case, G1 will become weights of index and G2 will stay same, or add it to G2. So G1 will stay same or G2 will become weights of index. In which way, start considering elements from the index plus 1 next time onwards. The base case is when index has become n or it has become equal to weights dot size. In that case, you update the answer, right, and just simply return. Now, how do you interpret this recursive function? Like the way you can interpret this recursive function is, let's say for the 0th guy, you can either include in group 1 or group 2. So when you include in group 1, what you're doing is you're calling this function and saying, okay, I have included the 0th guy to group 1. Now you go and find out all the partitions in which I have put the first guy or the 0th guy into the group 1, right? So all the possible calls for, you can say, if I want to show you the recursion tree that we have, you can clearly see that all the possible calls below this will have like all the possible calls here will have the 0th guy in the first partition, right? So that's what I'm saying. I'm calling this function saying, okay, I'm including this first guy in the group 1. Now all the partitions here will have the first guy in group 1. Similarly, all the guys here will have first guy or the 0th guy in group 2. That's what I'm doing. Fine. So I mean, yeah, that's about the code part. And the time complexity, I guess it goes without mentioning. The time complexity here is order of 2 power n, and the space complexity, we are not using an extra space, but the recursion stack, so it will be order of n. And that's about this. I hope you liked the video. Like, if you did understand, if you did get something out of this video, please give it a thumbs up and let me know your thoughts if you have any suggestions or anything. I'll see you in the next one.